Let's think about the excited states of molecular vibration now. So we have our simple harmonic oscillator. We figured out the ground state, that the wave function looks like a Gaussian, that the energy is 1/2 h times the characteristic frequency nu. Now let's go for the excited states. So first of all, let's sketch out our potential here. Let's get a little more room. Sketch out a nice little parabola. So I've got 4, 9, I go up, I can get 16 there pretty easily by taking 9, and the distance to 4 is 5, and then a little more for 1, and I can draw a nice little parabola there. So that's our potential. V is equal to minus 1/2 kx squared. K is the second derivative of that potential. And let's slap in some states here. So we're going to have an energy E0, we figured that one out. There are going to be a couple more states. They're going to be higher in energy. Let's just toss them in like this, E1, E2. Okay, so first thing is we expect the nodes to be related to the state number plus 1. So the first ground state's going to have no nodes. First excited state's going to have 1 node. Second excited state is going to have 2 nodes, etc., etc. That seems to hold pretty well. So we have to cut down the middle here. There's going to be some symmetry. And for the first excited state, we expect the node to be right in the middle at the point of symmetry. And for the second excited state, we expect 2 nodes on either side of the middle, but an extremum right in the middle. Those are basically the choices right in the middle. The wave function can be at an extremum, or it can be going to 0. So those are the demands of symmetry, and we're going to have odd and even functions about that. Okay? The second thing is the classical turning points. So the turning points we saw with the first, the ground state, become inflection points. So the curviness, psi double prime over psi, changes sign. Psi double prime is equal to 0 when we hit those classical turning points, which I'm now marking in red here. So those guys, again, they're classical turning points, and that's the hint that in quantum mechanics something's going to be a little bit different, and the wave function doesn't go to 0 there. It's the second derivative of the wave function. It becomes straight at those turning points. So we can sketch out the ground state wave function according to that. Now also, the steepness of the wave function at that turning point is going to have something to do with the derivative of the potential. And here's what I mean. For the particle in the box, the potential was straight up, the derivative was infinity, and that caused everything to shut down real fast. So we had some energy level there, a classical turning point right where we hit the wall, and the wave function was quite steep right at the edge, and it actually had a kink because it had to go to a hard 0 outside of the box if the potential was infinitely high there. Whereas if the potential is sort of shallow, let's say angling off like this, then at the classical turning point there might be the derivative will be somewhat quite a bit less, and we expect a rather smooth transition from a downward curving to an upward curving wave function as we go outside of the classically forbidden region. So we can make use of that now and expect a relatively shallow inflection there on the wave function corresponding to that state E1 with energy E1, and I'm taking advantage of the fact that because of the node in the middle, I know it's going to have to be above 0 on the left-hand side and below 0 on the right-hand side, so I've got a matched pair there. And so the wave function's got to look something like this. It's going to go up, gradually inflect at the classical turning point, hit a maximum, go through 0 at the midpoint, that's our 1 node, go down, and then inflect again at the second classical turning point and decay away more or less exponentially toward the value of 0, well outside of the classically allowed region. The value of the wave function does have to eventually get to 0 because you just can't be too way out there. Now the second excited state is going to be steeper at the edge. This one's going to be symmetrical about the midpoint because there's 2 nodes, so I expect 2 upward going values there. And then we're going to go from 0 up, make a maximum, cross 0, go down, make a minimum right in the middle, the symmetrical point of symmetry, and then we turn up again, go through the 0 point, hit another maximum, go back down, inflect, go to 0. That's the basic idea. Notice as well that the maximum amplitude is over near the edge, and that's because over near the edge the the total energy, the kinetic energy isn't very large. So psi double prime over psi is fairly low. The kinetic energy is low, but that also means that you can think of it as moving slowly, and so you expect when it's moving slowly, that ought to be where the probability of finding the object, which is the amplitude of the wave function squared, is at a maximum. Conversely, in the middle there, the curvature is relatively high, but the amplitude of the wave function is small. Because there it's moving really fast, it's got high kinetic energy, and so the probability of finding the object is correspondingly lower, because the kinetic energy is way down from the total energy down to the zero there. So those are the various constraints we can put together from what we know about quantum mechanics now, counting nodes, paying attention to the relative curviness given by the Schrödinger equation, paying attention to symmetry requirements, paying attention to the boundary condition that the wave function does have to get to zero eventually outside of the box. We can construct basically what these wave functions are going to look like. Now, without further ado, here's what the wave functions actually are. It takes a long time to derive them. They always have that ground state solution, that Gaussian in them. And we tend to write them in this way. The wave function psi is a function of the quantum number, which is now v, is equal to some normalization constant, n of v. There's a thing called script h here, h of v, and we'll see what that is in a second. It's going to be a polynomial. And then we have a Gaussian type term, but we're going to write it as e to the minus 1/2 xi squared, just because I love trying to write xi. It's my worst Greek letter, but that's the one we use. So the vibrational quantum number goes 0, 1, 2, 3, 4, 5. So we've been calling the lowest energy the ground state. We've been labeling it 0, and that's because, in fact, that's what's done. So we're going to use the lowercase v for the quantum number for the vibrations, but we're going to start at 0. So their integer values allowed starting at 0, 1, 2, 3, etc. This value xi is a non-dimensional unit of x. So it's x divided by sigma, x divided by the standard deviation of the Gaussian function. So xi essentially says how many sigma away from the maximum point, the midpoint, are we? And so that's how everything scales in the problem. Remember, sigma squared is h bar divided by the square root of the spring constant times the mass, which is equal to h bar divided by the square root of the second derivative of the potential times the mass, because the second derivative of the potential is equal to the spring constant. I hope if I repeat that enough times, that'll become second nature. So these h's, these are called Hermite polynomials, and once again we find that they're polynomial solutions. Basically what happens, and you can follow this through some in the notes, and you can look it up more online if you're interested, is you put this in as a test function, and the Gaussian part, the e to the minus 1/2 xi squared, winds up canceling out all over the equations, just like it did in the ground state, and you're left with sort of residual polynomials that gather everything together. And there are various ways of building them up, but it's a fair amount of applied mathematics, and we're just going to say that they exist here. So h0 is just 1, so that's for v equals 0. h1 is equal to 2 xi. h2 is equal to 4 xi squared minus 2. h3 is equal to 8 xi cubed minus 12 xi. There's an interesting thing to notice here. When the vibrational quantum number is even, then all of the terms in the polynomial are even. So h0 is 1, which is really xi to the 0, and that's even. h2 has a 4 xi squared, that's an even power, and then there's a 2, which is really xi to the 0. And the maximum power coefficient of the polynomial is equal to that quantum number subscript. So for the h2, we get a xi squared term. h1 goes like xi to the first, and that's odd. And h3, there's a xi cubed and a xi to the first term, which is odd again. The other thing is, you notice that the even Hermite polynomials have only even powers of the non-dimensional x, the value xi, and the odd Hermite polynomials have only odd powers of Xi. And that's necessary for the symmetry, because take a look at this, because since there's always a Xi in the odd powered one, that means if Xi is 0 in the midpoint of this, that's going to go exactly to 0. So that's guaranteed to set this thing down to 0, always. And correspondingly, the even powered ones always have exceeded the 0 term, which is a constant, and they don't go to 0. And because they have no odd powers, they're guaranteed to be symmetrical about the midpoint. So that sets up the symmetry of the whole thing as well. The energy levels for the vibrational quantum number are h nu, where nu is that characteristic frequency of the vibration, times the quantum number v plus a half. It's that simple. We had 1/2 h nu was the energy for the ground state, so we already got that one. And each time you add in another quantum of excitation, a quantum of vibration, you just get another characteristic frequency's worth of energy. And that's pretty consistent with the idea that a vibration always has the same frequency. So that this ladder of states is really characteristic of the harmonic oscillator. So they're evenly spaced. It's like a perfect ladder. You have 1/2 h nu as the 0 point, and then every subsequent state goes up by nu. So here's our potential again. We've got the ground state at 1/2 h nu. We give that 0 as the quantum number for it, but the really important thing is it's 1/2 of the characteristic frequency up from the bottom of the well. The next state is up by h nu. The next state is up by h nu, the next state is up by h nu, and so they're evenly separated all the rest of the way up. So there we go, 0, 1, 2, 3, 4, and I could keep going 8, 9, 10, 11, 12, all the way up into the stratosphere for the simple harmonic oscillator case. So I'd just like to break down the wave function one more time, just to look at how these things play. So we've got the wave function psi of the quantum number v is psi, sorry. The wave function psi of the quantum number v is some normalization constant, Hermite polynomial, and then this Gaussian term, e to the minus 1/2 Xi squared, for any quantum number 0, 1, 2, 3, etc. So let's draw the x-axis here. And what's going on is the polynomial is responsible for the wiggling, and the exponential, the Gaussian, is basically responsible for making sure it goes to 0 as we head out to a large absolute values of x. So here's some random polynomial, and I'm drawing it an oddly symmetrical polynomial, so it's got to be h7. There's 7 nodes, 1, 2, 3, 4, 5, 6, 7 there. It's an odd polynomial, so it goes down for large negative x, and it goes up for large positive x. Polynomials always do that. Eventually they're going to go to infinity, and when you have high order polynomials, very often, especially the way these ones are set up, they wiggle a lot in the middle, but then eventually the last term, in this case it's going to go like c to the 7th, is going to blow up. It's always going to beat out the other ones, and so it's going to rush off to infinity, and we've got c to the negative 7th on the left-hand side below 0, and so that's going to go off to negative infinity. So the polynomial wants to blow up. It wants to go up to infinity. That's not good news if we're going to try to normalize a wave function. But then this Gaussian term comes in and just says, oh, okay, everyone, chill. So we're going to focus on the wiggles in the middle, okay? And no matter where we are, those 0 crossings in the polynomial are always going to get me a 0 crossing, but basically I'm going to get everything calm down, heading towards 0, and exponentials always win. So if I have an exponential times a polynomial, and even though the polynomial is going up toward infinity and the exponential is going down towards 0, the exponential going towards 0-ness beats out that polynomial trying to get up to infinity, and it's going to calm it down and make it go down towards 0. So exponentials always win. And that's the way the math kind of plays out in the situation for the wave functions.